Now we look at abstract Boolean algebras with their laws and the axioms. So this is different than when we were just talking about the Boolean functions. But if you need to come up with different ideas of figuring out these identities and these laws, you can just go back to when we were talking about the Boolean functions. But the Boolean functions are a specific type of abstract Boolean algebra. So what is an abstract Boolean algebra? It's a set B that we will call B that contains two disjoint elements. There's going to be a zero element. I put this in quotes because it doesn't have to be that zero that we always were using in the Boolean functions, but it has a zero element and a one element together with binary operations of addition. I'm going to use this for my multiplication symbol here, and the unary operation of complementation. And I'm going to go ahead and use this for my complementation notation as well, but we can use the bar for the complement. And it's going to satisfy for all x, y, z in this abstract Boolean algebra 5 axioms, or your book might just call them properties, but these 5 axioms must hold. We have x, an element x that's in the Boolean algebra, added with the 0, so this is the 0 element, will give you back x. Then x multiplied by the 1 element will give you back x. And those are called the identity laws. The first one is the additive identity, and the second one is the multiplicative identity. Complements law. We have x added to its complement needs to give you back the 1 element. X times its complement will give you back the 0 element. So that's the complement law for the sum and the product. So again, think back to the Boolean functions, or you can go back to those videos to look at how we're using propositional logic with that. Associative laws. This is for the Boolean sum and product. So we can just regroup. So notice our parentheses in the first 2, and then we put our parentheses in the second 2 elements when we're doing our sum, our addition. And you can do the same with multiplication. Then we have the commutative laws. That just means we can reverse these orders in the addition or the multiplication. And then this distributive laws. So we can distribute the x plus to each part. So again, this means multiplication here. So we end up with x plus y, then the multiplication of x plus z. So I did leave out the multiplication symbol, and that's okay. You don't have to have that multiplication symbol in there all the time. It'll be understood to be there. So these are your distributive laws. So once again, for a defined Boolean algebra that we have here, so we have a set and we have our operations and then our 0 and our 1 element, it must follow the 5 previously listed axioms. So for example, I wanted to give you some more on the notation, and what we could have said is there is an element, and you can call that element, say, z, and again, that's because it's known as the 0 element. But I just don't want you to get confused because it's not always going to be that real number 0 that we're used to. So there's some element that's called z in the set B, such that if you take an element A in the set B and you do the OR, so A or that 0 element, it will give you back A. So again, you can think of like the power set. So if you're starting with your power set, what would be that 0 element? Well, any element in the power set, when you OR it with the empty set, you'll get back that original set. So this 0 element, for example, if we're dealing with the power set, we would end up with the empty set there. And then there's going to be an element u. So again, instead of saying the 1 element, but again, that's what we'll usually be calling it, but I put it in quotes just because it's not always going to be that real number 1. Some textbooks will call this u. And again, that's for the unity element, the one element. So there's some element U in this set where when you AND it with this unity element, you'll get back the original value. So like again, in the power sets, what you'd have to do is so this is for any element A in the set B, you would have to AND it with the entire set itself. So that unity element would be, the entire set that's given. For every element A, there is an element A prime here, such that A or this A prime is going to equal the unity, and A prime is going to equal the 0 element. So that's another way that we could use this in the notation. So you might see this listed for an abstract Boolean algebra versus what's listed up here in our textbook. Again, everything is still the same. It's just that now we are looking at, just generalization so that we don't always think of the regular 0, the regular 1, the regular addition and multiplication. So you can think of it, again, using that Z 0 element and that U unity element. So it still has to follow those 5 axioms listed that we had before. It's just that now you might want to replace that, or just, again, think of that as being, instead of that 0 put in there, it's just some Z element. And instead of this 1, it's some U element. And again, those elements are coming from this set. So it has to satisfy these properties going throughout. So these properties and axioms can hold for other sets as well. We can call them B. So we generalize, and another word for that is to abstract to other algebras. So we use the binary operator. So again, binary operator just means that you're going to perform this operation on 2 elements from the set. So we're going to use that addition and the multiplication, as well as the unary operator. So that's performed on 1 element, and that's the complementation. So the only thing is now each algebraic structure, so again, these are just rules that you have to follow. This is an algebraic structure, rules that you have to follow. It'll have its own rule. It will have its own definition of these operations. So you just have to follow what it says to do when you need to add, multiply, or do the complementation. So if you have this set where you have a set B with the addition, multiplication, complementation, as well as a 0 element and a 1 element, if it follows those axioms that we had listed, then it's called an abstract Boolean algebra, which means all those laws that we had before, all those Boolean identities and laws, do hold on that algebraic structure too. So you're able to generalize, and you don't have to test again for that specific algebraic structure. And that's why when we were looking at proving, we were just using the variables. Instead of a specific set, we wanted to make sure that if we had x plus, say, x complement, what are we supposed to get back? Well, if you have x plus x complement, we should get back a 1. So we looked at some of those rules, and we just prove it in general instead of just thinking about, okay, what if I had a 0 and a 1? So we're thinking outside of the box. We're not just thinking about, before we were using B just to be the set 0 and 1. And those are the Boolean functions, but we can now extend this further besides just the set 0 and 1. Okay, so from this point, we want to notice that we will also be defining the Boolean algebra in terms of what's known as a complemented and distributed lattice. And remember, that was a partially ordered set, and it had a least element and a greatest element. So we're going to be able to have an ordering on our algebraic structure. We're going to have a least element and a greatest element, so we'll be looking at the Hasse diagram. And that's why sometimes we call this 1 element the top element, and that 0 element the bottom element. And it should start to make more sense when we do the Hasse diagram and we talk about atoms and how are we building these sets in this algebraic structure. Okay, so I've copied down again, this is what we had before. These are the 5 axioms of properties that we're trying to satisfy. So we have the 0 element and the 1 element. And I like to put those in quotes because it doesn't have to be a 0 and a 1 anymore. It just depends on our structure, on our set. But it does have to satisfy these laws. So it does behave like the 0 and 1. Whatever this happens to be, if I add it to an element x in the set, it better give me back the x. Okay, so in this case, what does the 1 do? The property of this 1 element says when I multiply it by an element in the set, it should just give me back that element in the set. So, and then complementation as well. And we're going to get back, the other laws like I was mentioning before. You're still going to get back the laws that you can prove, like the domination law and all those other ones. So again, let me just reiterate, you have to have these 5 axioms, these properties satisfied. So I need to have this 0 element and this 1 element that's in this set B in your Boolean algebra. And as long as these 5 axioms are satisfied, then you will have your abstract Boolean algebra. So here's some examples. We can have the set B with the elements of 0 and 1 with the 3 operations of addition, multiplication, and I'm using the symbol here for complementation. So we dealt with these in the Boolean functions videos, and we did notice that all 5 axioms did hold, and we were able to come up with some more identities from that. Also, number 2, b to the k with the 3 operations that we define here. So I'm listing these 3 operations as a, b, and c. So if we take the set b to the k and we use these operations of addition, just term-wise, basically entry-wise, so entry-wise addition, and then multiplication, again, entry-wise, and complementation, entry-wise. So if you look at this one, for instance, what is the 1 element here? Well, the 1 element is not just going to be 1 like we had in our first example. The 1 element has to be the 1, and this would be k1s listed here. So k of these number 1s, that would be the 1 element. And it does satisfy the identity and the complement laws. So if you wanted to verify this, you would just verify it satisfies the identity and complements law. So notice that if you take a plus this 1, you're going to get 1 back. So when I say a, I just mean take an element. So maybe I should just write it down here. I'm going to take 1 element here coming from the Boolean algebra, and I'm going to add my 1 element to it. So this is the 1 element. And notice you do get back 1. So it looks just like this identity says. If you take an element in the Boolean algebra, you add 1 to it, your 1 element, you get back the 1 element. So we also end up with the multiplication being satisfied, the identity for that. If you have your element times the 1 element, you get back your element. Okay, and also the complement law. If I have my element plus its complement, so this last one here, the element plus the complement, I'm just separating it by the definition of adding. So I'm adding term-wise, adding term-wise. But notice if you do x sub 1 plus x sub 1 complement, that is going to give you back 1 in every position. So think on your own what you would get back for the 0 element. So what would be the non-0 or non-1 element here? It would be, just anything in the set which is not the 0 element and it's not the 1 element. So, maybe if I had 5, like if I'm doing B5, the 5 tuple, I could say, why don't I do 1, comma 1, comma 0, comma 0, comma 1. I mean, that would be an element that is neither the 0 element nor the 1 element. So b to the 5, has many elements in that set. And this would just be one of those elements in the set. Another example, number 3, would be the bool k. So this is the Boolean functions of degree or order k with the 3 operations that are listed here, A, B, and C. So these are our 3 operations. So notice we dealt with these like the Boolean functions of degree 2. We had 2 to the power 2 squared, so we had 16 of them if we looked at the different types of Boolean functions of degree 2. And we did those in the other videos. But here, what are those 3 operations? Well, if we have addition, or again, with addition and multiplication, you can think of the conjunctive and disjunctive here. But I'm going to have adding of the 2 functions is just going to be f of u plus g of u. And then a multiplication is just going to be their product. And complementation, you're just going to take the complement. Another example is the set of all functions with the domain S and the codomain 0, 1. Okay, so what that means is you're going to take your set S and it's going to be mapped over to just a 0 or a 1. And the 3 operations we can define as A, B, and C. Addition is going to have you start at your set and map over to 0, 1. Multiplication, same. And for your complement, again, you start at your set and you map it over to 0 and 1. So what do you think the 0 element here would be? Well, since we're dealing with the functions, this 0 element is going to be what's known as the characteristic function. So this is known as the characteristic function. And this one is going to be of the empty set. So why is the 0 element here the characteristic function of the empty set? So this is how you denote it, like this. It is the set that starts at S and it maps it over here to B, where it's defined to be, and when I say this, it's actually 0, 1. The characteristic function for us is going to be map it over to 0, 1, but in general, x sub a is going to be 1 if x is in the set A, and 0 if x is not in the set A. So if it's in S minus A. So that's how you define a characteristic function. A characteristic function will say, let's go ahead and map all the elements that you take from the set A to 1. And then all those elements that are from some set minus that set A, you're just going to map them to 0. So ours, for example, and again, B is going to be 0, 1. It's just mapping over to a 0 or 1. It's going to be the empty set. So for the empty set, what we're going to have is the characteristic equation is equal to, of the empty set, 1 if x is in the empty set, and if x is not in the empty set, we're mapping it to 0. So notice I'm going to have to check those 3 properties to make sure that this truly is going to be our, like we said, this should be the 0 element. If it really is the 0 element, let's see if it satisfies the identity and complement laws. So here, let's look at the identity laws, these 2, and then we'll look at the complement law. Okay, so on top, f plus g. So remember, f plus g means it's going to, I'm just telling you what addition is. This is how you add, but what I want to do is I want to take some function f and add it with my 0 element. Okay, so what I've done is I've taken a function f and I'm now going to add it to my 0 element. So here's f plus my proposed 0 element. If I add 0 to a function, what do you think we're supposed to get back? We're supposed to get back that function. So do you get back that function? Well, what does this mean? This means that I'm looking at an x that is not in the empty set. So if the x is not in the empty set, what is that function going to be? The function is going to take on the value 0. So if I have the value 0 here, then I'm just going to get back the function. So yes, that's satisfied. On the second part, I have multiplication. So with the multiplication, I look at the same. I put in my proposed 0 element. So I'm going to have my function times my proposed 0 element. If I multiply a function by the 0 element, what am I supposed to get back? I'm supposed to get back the 0 element. Do you get back your 0 element? Yes, and for the same reason. This is for all x, not in the empty set, so it's going to take on the value of the characteristic equation of the empty set. So it is going to be this value. And for the last part, this is the complement. For the complementation, what do I need to check? I need to check that if I multiply the complement of the function times the function, then what should we end up with? The 0 element. So notice what happens. If I multiply the complement of a function, remember the function was mapping, let me go back. The function here was mapping over to zeros and ones. So if I take some function that maps to 0 and 1s and I take its complement, then one of those is going to be a 0 and one of those is going to be a 1. So the complement times the function, you're going to get this pattern here. And you can use the commutative property. It's going to be a 1 or a 0 in either of those spots. But they're going to get multiplied to give you back a 0, which is the characteristic function of the empty set. And here's an example where we have the power set of S, of a set S. We have our 3 operations, so how are we going to define the addition, the multiplication, the complementation on this power set of S for this Boolean algebra? So for this Boolean algebra, we are going to say that the addition means you're going to take the union of the sets A and B. For the multiplication, we're going to take the intersection. And how are we going to take the complement? Well, the complement of A is going to be everything that is outside of that set. So that is what we're going to do when we take the definition of addition, multiplication, and complementation. So we've seen this before. We've done this before. Now, what is the one element in this set S then? So remember, if you go back to the rules that it has to satisfy the identities, it said that if I add a 1 to an element in this set, so let me just say that we have a set A. We're just going to take a set A from our power set of S. If I take a set A from the power set of S and I add this one element to it, what am I supposed to get back? Well, it's supposed to give you back 1. That was the rule. When you take an element in a set, you add the one element to it, then you get back 1. Okay, you OR it with the one element, you get back 1. So what else was it? If I take the set in the power set of S, any element that is, and then I multiply it by this one element. So now we're doing multiplication. You're doing the and. What am I supposed to get back? Well, I'm supposed to get back the set. So that's how the one element is being played here. You can also look at the one I was talking about before. If you take the set A and you add its complement, then what are you supposed to get back? So if you OR it with its complement, you get back the one element. So what is playing the role of the one element in the power set? It would be the set S that you're taking the power set of. Okay, and the reason is you can just verify. If I take a set A, which is in the power set of A, but I add the entire set S that I took the power set of, so remember addition in this algebraic structure means to take the union. So if I take the union, what do you get back? You get back S. And then if I take A, I'm just going to do the next one, a set A, which is in the power set of S, and I multiply by that set S we took the power set of, what does it mean to do multiplication? It means that I do the AND statement here. So if I do the AND, the intersection, then I get back A, okay, because A is going to be in the power set of S, so it has to be the whole set or smaller than that. So A is going to be the result there. And notice it does follow that property, and this property is satisfied. You get one here and one here. Okay, so the set S is behaving just like that one, is playing the role of the one. Oh, and I can check this last, I'll just check this last one as well, because these laws hold too. If I take A plus A complement, so the set A plus the complement of A, so this is again the union when you add, that is going to give me back the set S, the entire set S. So think about what would be the zero element here. So go back to the properties, go back to the laws, those axioms, and think about what would be the zero element when you're doing a union, an intersection, in order for it to give you back the correct values for the zero element. And here's another example. So this one's more interesting. So we look at D sub 6, where this is the set 1, 2, 3, 6, but you have your three operations defined below. So if you're going to be adding two elements from the set, what it's going to mean to us is it's going to mean to take the least common multiple of those two elements. If we're going to be multiplying two elements together from the set, we're going to want the greatest common divisor of those two elements, the GCD. If we need to take the complement of an element in the set, we now are going to have 6 divided by the element. So this is thinking differently, but it does satisfy the 5 axioms that we had listed for the abstract Boolean algebra. So you can verify that those 5 properties are satisfied. And let's think about what the zero element here would be. So it's interesting that the zero element is now the element 1 of the set. So the zero element is the element 1 here. And why? So how do we check this? Remember, we check that the identity and the complement laws are satisfied for the zero element, and we do the same when we do the 1 element. The only difference is when we do the zero element, again, I'm going to look at the complement law as A complement times A to see if I get back the zero element. But let's start with the identity. Let's see if it satisfies the identity properties. So to start with, what I want is I want to look at taking an element A, and I'm going to add my zero element. So remember, we're going to be adding, this is what I am proposing is the zero element. If I have A plus the zero element, I need to get back A. Well, let's see if it works. A plus 1, would that give me back A? Well, what does it say to do if I'm adding? If I'm adding, I'm really taking the least common multiple. So A plus 1 is the least common multiple of those two numbers, A and 1. And what is the least common multiple of A and 1? Well, it would just be A. So far so good, that works. Now I check the second identity for multiplicative. If I have A times my zero element, so this is my proposed zero element, A times my zero element should give you back the zero element. So what does it mean when I multiply? Well, now according to this, multiplication means get the greatest common divisor. So I need the greatest common divisor of A and 1. What is the greatest common divisor? What will divide into A and into 1 at the same time? Well, just 1. And 1 happens to be the proposed zero element. So that means it's working. Okay, so far it's satisfied the identities for the identity property. Now I have to check the complements law. If I look at the complements law, this last one, an element A from the set, take its complement and multiply by A. What should we end up with? We need to end up with 0, the zero element. So let's take A complement. So A complement means I need to take 6 divided by A according to this third operation here. So 6 divided by A, and then I'm going to multiply A. So what does multiplication mean? So don't, cancel, you don't cancel these out because that's not what multiplication here says to do. Remember what multiplication in this Boolean algebra says to do. If I'm multiplying, I am finding the greatest common divisor. So now I have a 6 over A, that's my first element here. I'm multiplying it by A, so now multiplication means find the greatest common divisor. So what's the greatest common divisor of the first, 6 over A, and A? Well, if it's going to be, if 1 is going to be my proposed or my true 0 element, it needs to give me back the 0 element. Okay, remember we were checking if we're doing the multiplication. A complement times A, according to the complement's law, needs to give us back a 1. No matter, how you're defining that multiplication, if it's a Boolean algebra, then it needs to give you back a 1. So let's check them. So we're going to check our cases, because when we multiply, it says that I need to find the greatest common divisor, and that changes as your element changes. So I'm going to check for A equal to 1, A equal to 2, A equal to 3, A equal to 6. Let's check 6 over A and A. So what's the greatest common divisor of each of these? Well, we get the greatest common divisor of 6 and 1, which would be a 1. Greatest common divisor of 3 and 2 is a 1. 2 and 3 is a 1. And 1 and 6 is a 1. So notice every time we get back a 1. So yes, this is satisfied. So the 0 element here is the element 1. And so why don't you think about what the 1 element would be here for this abstract Boolean algebra?